Alright, hello everyone. I am going to attempt to give you as thorough of a tutorial as I can about the cleaning and merging session that we had this morning, so that you can have some time to really be able to pause, look at things, go over. There's going to be things I'm sure that you'll take away from this and you'll see that you can perhaps use it right away, and other things that you might not see very useful. And that's just how a lot of these kind of coding experiences really work. But my goal today is to be able to show you how I'm going to take two data sets that come from the Alzheimer's disease neuroimaging initiative, and how I can try to clean them and then merge them. And you could think to yourself, why don't I merge them and then clean them? And you could, but you might run into issues kind of going about that approach than the other, as we'll kind of run into here. As even though I believed that I had cleaned these data pretty well, when it came time to finally merge them, I realized that I had missed something. And this is a data set. It's not mine. I was able to fill out a data use agreement. I was able to then be able to be given the data so that I can then work with it for the proposed reasons that I submitted my agreement to do so. And I'll just kind of show you how I would kind of approach my research question here. Is are there any longitudinal changes in cognition based upon certain demographic variables? And so for this exercise, I'm going to look at if the total score of the mini mental status exam changes over some longitudinal period within this cohort, and if there seems to be any kind of difference in that level of change over time between males and females. So first thing I'm going to do, this is a fresh session, so that you'll see that I'm going to be loading my libraries first. I'm only going to kind of use ggplot2, because initially I thought, I probably won't need any special functions to be able to really work with these data. I could use a lot of base functions, but I'm going to do all my visualizations with ggplot. And then I'm going to set my directory. So you can see it updates here. It's going to my ADNI directory. And then I'm going to load my data. And these are going to be .r data files. Okay, so they're going to be loaded in fairly easily. They're going to be loaded in as their names. This one represents the demographic data of the participants, of which there are roughly 4,800 observations, and then the MMSE data represents the longitudinal kind of measurement of my cognitive variable, the MMSE, across many time points, right? And that's what I kind of know about it at default, face value, and why I wanted to work with this data set is because I knew that it had a lot of people, it had measurements that I was curious about, and it did it across a long period of time. So first thing I'm going to do is kind of get acquainted with the data. I want to kind of figure out what is in my data, what are in these data, and then be able to kind of establish a workflow from there. Okay, so what I'm going to do is I'm first just going to print all the names of my variables in here. And I have 31 variables. There's only probably a few that I really care about, right? So I'm going to keep age, I'm going to keep handedness, I think, is one that I'm interested in as well. I'm also interested in, my project's going to be on gender, so I'm going to include gender as well. So I have handedness, I have gender, and I'm also going to keep education, which is somewhere in here as well, right there. So I've been able to identify those, and now I'm going to also, by looking at the data dictionary, which I have here online, I can look and see what some of these other not so clear type of variables are. So one of them is this vis code, and this stands for the visit code. And if I'm just going to want to understand what types of visits are within a variable, I'm going to use my unique function here. And what this does is just going to give me all of the unique entries within this variable vis code. And what I can see here is that I have several types of visits. I'm probably will take me a little bit of time to kind of figure out all these, but some of these are pretty intuitive. I can then also say if I perhaps see baseline versus screening, right? I might be a little confused about which one of these I would want to use. I can then the council just quickly do table PT in this code, and then it will tell me which one I have more of. So in my screening, let's see, it'd be an SC, I have many of those. So it looks like I have about 3,675 individuals in this data set, whereas my baseline only have 9. So I'm already beginning to see that perhaps this isn't going to be a super clean data set at the get-go, even though this is a data set that has millions of dollars invested into it, with many people working on it to be able to try and harmonize it as best they can. But nevertheless, I have some rather kind of head scratcher things here, right? So, clearly there's some longitudinal data in here as well. It seems to go out to about 90 months, if that's what I'm going to assume what M means. But somebody put in baseline potentially as what this is, and perhaps that means what screening is, but I'm not going to maybe take too much of a leap of faith that that's true, so I'm just going to keep the screening ones. So I'm going to create a new data frame that is only going to keep the screening types, the type of variable within VS Code that matches screening, and that's what this logical is. So when you see this double equal sign here, that means give me all of the all of the type of the VS Code variable that matches exactly to SC. So if I were just to run this, what it's going to do is it's going to kind of work through this kind of, it's going to return what's called a Boolean, which is just going to be a true or a false. And since I told it just give me the exact matches of, it's only going to then return all of the rows that exactly match to SC and then leave out everything else. So when I run this here, I can see that now I have 3,675 observations, whereas before I had 4,806, but clearly not all of those were SC, so I'm only keeping the SC. Now I want to know how much missingness is in my data. I want to do this across all of my columns, right? So I have 31 variables here. I want to see if I'm perhaps missing more data in one column than I am in another. So maybe age has a lot missing, or maybe gender has a lot missing. Perhaps pretty unlikely, but perhaps possible at the same time. So what I'm going to do is I'm going to first use this apply function on my new data set. I'm going to tell it, okay, across the second dimension of my data set here, all right? So if it's a matrix, if it's a data frame, it has 2 dimensions. The first dimension is going to be for the rows. The second dimension is going to be for the columns. And then I'm going to say across all of the columns in my new data set, apply the is.na function. And what this is going to do is it's going to give me, again, a matrix of all of the true or false if the observation within that variable in that column is in fact an NA, or if it is not an NA. And if it is an NA, it will label it as true. If it's not an MA, it will label it as false. Then what I'm going to do is to be able to understand the total quantity of missing values within each of my columns, I'm going to use the function call sums. And this is going to sum up all of the trues, and you treat the trues as ones and the falses as zeros. It kind of does that implicitly. Thankfully, I don't have to convert it into a numeric or anything like that. And this is what I get. This is a pretty nice readout, right? So I can see that I am, if I can find age here, I am missing 11 people do not have an age variable, right? Which is not that many compared to the total number I have. So now I have a decision I can make. So should I just remove the NAs, or should I replace them with perhaps the mean age value, right? So if I want to kind of do the easy thing, I'm going to say I'm just going to remove the NAs from it. So I'm going to create a new data set. It's going to call demo sc no missing age. And within my data set that now only has the screening visits, I'm again going to use this is.na function, just like how I used it here. And this is again just going to return a true or false for if the value is or is not an NA. But when I put an exclamation point in front of it, this means basically reverse it, right? And so what I'm going to do now is when I include the exclamation point in front of my is.na, it's telling it to convert all falses to trues and all trues to falses. Now, why would I want to do that? Well, because I only want to keep the values that are not NA. Is.na is going to return all of the values that are NA. So in order to keep all of the values that are not NA, I have to convert all of those falses to true, and then I can index it again just like I would here. And as you can see, my index here, and I should have perhaps explained this a little bit earlier, is that when I have my, let me clear this. Oh, I see why it's not there. There's my broom. Okay, so when I'm indexing a data frame, right? So let's say I just want to do in the first column, in the first row in the first column, right? That's just going to give me the very first value within my data set within that first column. If I do say give me the first observation across and then I leave it blank like this, that means across all of my columns. So when I run this here, now it gives me the first index across every column in my data set. And then I could also reverse that and say give me all of the observations in the first column, right? And it will just then print out all of the observations of that first column, and of course kind of remove some or omit some from being displayed if I have more than 1,000 entries. Alright, so that's what I'm doing here, is that I am going to be indexing into my data frame here, telling it to only give me the variables that are not NA across all of my columns. As you can see, this empty space here. So now I have my demo only screening, no missing age variable that has now removed those 11 participants that had a missing value. And I'm always going to really recommend that try to find a way that you can perform some kind of sanity check for yourself. So when it comes to doing kind of removal of data, you want to make sure that what you did is actually what you intended to do. So I'm going to rerun this same function just like I did up here, but now on my new data set. And I should expect to now see that in age, where I did have 11 missing values, I now have 0. Okay, and I can also probably confirm that, you know, anything else that was kind of removed with it was probably decreased or stayed the same as it was before. So now, let's say that instead of, if I don't have a lot of data, I want to try to preserve, you know, maybe if I only have a couple hundred data points, and losing 11 might be a significant amount of my data, perhaps now what I would prefer to do is just replace it with the mean value, given if I assume that my the distribution of that variable that I want to replace with is normal, right? And so I'm just going to kind of now start to understand descriptively what the data is like. And so I'm going to look at what the mean is. Mean is 72 years old. Standard deviation is 8.2. So that seems to be within the kind of range I would expect for a variable for age to kind of go 1 standard, 2 standard deviations away from 72 by increments of 8 in either direction. It seems reasonable. It seems to be the type of range that I would expect. Now, of course, now if I print out the range, this is where all of a sudden I realized that, again, just as I was kind of getting hints at how kind of not so clean these data were, I am now observing that it seems like the minimum age in this, what should be an older, primarily older adult data set, I have a range of, I have individuals in this data set, or at least one individual in this data set that has a age of 0. Okay, so now I should have done what now I'm going to do what I should have done earlier, and I'm going to visualize the data. Now I see, here's this nice, you know, it looks like normal distribution here, around 70, which is where the mean is, so that looks good, but clearly there's something here. And if I were to now kind of zoom in on this, I can see that these are a couple, not just one, perhaps a few people who are listed as 0. So now I'm going to kind of figure out how many people I might have below an age range that I would not expect to be in this data set. So now what I'm going to do is I'm going to identify how many individuals in this data set are under the age of 55. Right? So what I'm going to do is, again, I'm going to apply this kind of logical operator to it. I'm going to say, okay, if the demo, if the age is less than 55, return true. If it is not less than 55, return false. And when I run that here, you can see that's what it does. Can't really do anything with this data looking at it like this, but now what I can do is I can sum it again, and it will give me the total number of individuals that have an age less than 55. And if I run this line of code, I have 14. Okay, so I have 14 people younger than 55, but exactly how much younger they are, I know at least a few are probably 0. So in order to really determine what is this kind of younger age range that I might be dealing with here, I am now going to try to identify the exact indexes of these individuals that have an age that is below 55. And what I'm going to do is I'm going to use this function which. So I have my logical here, where I'm going to say return true for anybody who's under 55 years old, or otherwise return false. And then tell me which indices within this vector match this logical. Okay, that's return true. If I run this here I have all the indices of these participants that are under 55 years old. If I then use this as my index within my demographic data frame for age, then what it will do is return the values of the age across for each of these indices. And I can see I have quite a few people who are right at 55, but also clearly I have 5 people that are age of 0, and then even one 24-year-old. So this is kind of confusing, unexpected for sure. Why one 24-year-old? Why are these zeros? When I got the data, that was not really a detail that was shared with me, right? And these are going to kind of be things that are going to be overlooked, right? There's always going to be things in data that is shared with you, especially large data sets like this, that are going to have, there's going to be something that was overlooked, and that's perfectly normal, right? There's always going to be something like that. I wouldn't kind of put that against anybody for something like that. So now that I know that I have this kind of funkiness just within age, maybe I should take a step back now and really kind of plot all of the demographic variables that I'm interested in a table, and be able to understand what are the age ranges, what are the percentage for my categorical variables, the frequency of my categorical variables, and so on and so forth, to better have a overall understanding of exactly what are these data like. And this is probably something I should have done at the very beginning, but you know, you live, you learn. So I'm going to use the same functions that we used previously when we worked on the demographics tables. I'm going to load GT summary and dplyr. And now I'm going to create just a simpler data frame that's just going to be called data table, and I'm going to use this function called subset, where from my original or my only screening visit demographic table I'm going to select the following variables here: age, PT gender, patient hand, and patient education category. And now I'm going to return that. So now I have my demo table. It only has these 4 variables within it. And now I'm going to create a table from my demo table with looking at, for all my continuous variables, the mean, standard deviation, the min, and the max. And then for all my categorical variables, the total frequency in those variables, and then the percentage across the total. So as I run that, it worked fine. I'm now going to look at the table itself in Viewer. I'm going to zoom in here. Okay, this is exactly what I saw when I was looking at before. I have my 11 unknowns, which is what I found before. My range is at 0 here. This looks normal, 48 to 52% male versus female. Left-handers, right-handers, 9% left-handed. That's kind of what I expect based on what we understand about the population. And then 13 unknowns. And then education as well looks pretty good. This would suggest that a kind of mean education level, if this is in years of a bachelor's degree, with some pretty kind of narrow standard deviation. But clearly some people who have a lot of education with a professional degree, and then people who have less education with what seems to be reporting here only 4 years of education overall. Okay, so this looks okay. I could continue to remove the unknowns across all of these. I'm really only concerned about gender for the most part, but I want to make sure I'm not including anybody into my data set that might be kind of, you know, I don't want to include a 20-year-old in here when I'm trying to talk about how this is an older adult data set. So I need to make sure I do my due diligence in that regard. So what I'm going to do is I'm going to remove all of these babies who are 0 years old and my 20-year-old by now indexing in here and saying, okay, if anybody who has an age greater than 50, go ahead and remove them. And so then I've removed them here. You can see now this has gone down a little bit more. And now what I will do is create a new data set called demo SC, no missing age. And again, I'm going to do the same thing to my earlier data set, right? So I had already removed the people who had no data, who had no age, and then I'm also going to remove now those individuals who are 0 years old or in their 20s, just to kind of clean up that earlier data set. So for my sanity check, I'm going to plot my histogram again for my age variable, and now I can see I have a nice normally distributed histogram within the age ranges I would expect. Nobody too young, nobody too old. I don't have anybody who's like 110 years old or anything like that. So it looks good. I'm pretty satisfied with the age so far. But again, the goal, as we set out to do about some 30 lines of code ago, is to be able to replace the missing ages with that of the mean. And so I'm going to create a new data frame called demo SC mean replaced. And then within my age variable, I'm going to identify all of the age, all of the NA values in my age, that is .NA. This is a super handy function. You're going to be using it a lot. And then I'm going to replace it with the mean age of my new data frame, and so that it's no longer an NA value, and now it's just going to be the mean of the age group. And that seems fine because this is normally distributed. If this were skewed, perhaps I would use the median, but it's normally distributed, so I'm happy with that. So I run that. I'm going to double check and make sure that I don't have any NA values within my age variable, and it comes out 0, so that looks good. I'm going to make sure that the mean hasn't changed. Why would it? I only replaced NA values with the mean, so it should stay exactly where it was. And now moving forward, I'm also going to remove people from my mean replaced data set that have an NA value for education and who have an NA value for handedness, just so that I have the full amount of information across all of the participants that I have. And so what I'm including here is, and why this is kind of interesting or helpful for when you want to kind of help remove cases based off of multiple criteria, is that what I'm using here is this operator, this logical operator known as the ampersand or the and. So what this is saying here is, give me all of the not NA values. Remember, I have my exclamation point here. And give me all of my not NA values for handedness. So give me all of the not NA values for education, and give me all of the not NA values for handedness across all of my observations, across all of my columns, and then create a new data set called demo final. And so I have demo mean replaced here, which is 3,668. When I run this, I am now at 3641, so I only lost about 27 people. I'm pretty happy still. I have 3,641 individuals. Now I'm going to trim down this data set to only include the data that I am interested in, which is age, gender, hand, education, and ID. I'll need the ID to be able to merge. So now I went from my 31 variables that I had previously to now only 5 variables. I'm going to double check how clean my data set is if I have any missing values across all of the columns, and I see that I do not. I'm pretty happy with what age is. I'm pretty happy with that. I know that gender was all complete, and I've removed any missingness within handedness and education. Okay, it's looking good. Pretty happy. So now it's time to merge. Finally, after 80 lines of code, now I'm finally ready to merge. I think I've cleaned enough to be able to now merge my data, or so we will see. And so now what I want to figure out is within my MMSE data, I'm going to look at the same visit code that I had before, and I just want to perhaps select the visits in which I have the most data, right? Because I had a lot of different visits there, and I'm sure I'm going to have a lot of visits that have varying degrees of data. I just want to work on the ones that have the most. So I'm going to order my table here based off of the least amount of observations to the most amount of observations. And what I can see here is that I have my screening. I have month 12, I have month 24, I have month 36, and month 48. I think those are the 5 that I'd like to keep. I'm going to ignore month 6. I'm going to ignore a lot of these other ones. I am going to run into what again is a little bit of a funny issue here, and that there's probably multiple variables that mean the same thing here, or multiple kind of levels of this variable that mean the same thing. So for example, month 12 is probably the same as y1, but nevertheless somebody put in y1 instead of month 12. Why? Who knows, you know? But it's only 2 observations. I'm not really going to try to convert a lot of these things into something that to try to maximize the amount of my data at this point. I could do that. It would be perhaps a little bit of a longer process to do that. But you know, I feel like just for this kind of cursory point of just trying to visualize my merged data set, I'm just going to select out. I'm going to remove all of the VIS codes that do not match screening, month 12, month 24, month 36, and month 48. Okay, and I'm going to do that with this kind of indexing now. So now I'm going to use, again, a logical operator to return all of the types of variable, all of the specific cases within my variable that match my criteria. So screening, month 12, month 24, month 36, and month 48. And the way that I'm going to do this, instead of using the AND, I'm going to use the bar, the horizontal bar, and this is going to mean OR. So the way that this reads is that I want to find all of the indices within my vector VIS code that are exactly equal to SC, or exactly equal to month 12, or month 24, or month 36, or month 48. So now it will find all of these instances for me, keep them, and remove everything else across all of my columns. Alright, so now my MMSE4, I went from 12,000 observations to 8,200 observations. So I removed basically all of these data up here, which I'm okay with. You know, a lot of these are just going to be in-betweens. It was probably going to not really improve the overall picture that I was going to be looking at. But that's just kind of my assumption that now I could always go back and change things, right? And as long as I know how I changed things as I was doing this, then these changes can be easy to make. So I'm going to look at my table again. I'm going to see that it matches exactly what I had up here before. I'm pretty happy with that. So I didn't lose anything. I didn't do anything incorrectly. I have all of my visits here that I want. And now I'm going to just out of MMSE4, as it has 77 variables, I'm only going to keep 4 variables: visit code, the patient ID, and the total MMSE score. Alright, so now I have my MMSE4 total data set that still has all those observations and 3 variables. Now I'm going to merge at almost line 100. So I'm going to use this merge function, where I'm going to say combine or merge MMSE4 total, my demo final, by our participant ID. So it's going to go through all of the participant IDs in MMSE4 total and all the participant IDs in demo.final. And it is going to identify all of those matches and then be able and then put them together into one data set that it's going to be called merge.df. Now when I run this line of code, you can see that I've somehow gained data, right? I would expect that I shouldn't have more than 8,227 observations. Now I have 9,152. So something unexpected has happened. And my suspicion is that I actually have duplicates in my demo data. So I'm going to run this. I'm going to now find out the total number of duplicates that I may have in my demo data. I'm using the function duplicated. This is going to again return if it's a duplicate, return true. If it's not, return false. I can already see there's quite a few trues here. When I sum up all those trues together, I have 209 duplicates. And clearly I cannot use duplicated data in my analysis or in my visualization. That would be an inaccurate portrayal of really what I'm trying to look at. So if I see here that I have added data from what I saw previously, now this is looking at my merge DF across visit code across this table here. It seems to be the case that now what I should do is create a new demo final 1. This is my kind of attempt at kind of now sloppy version control, in which case I'm going to remove all duplicated patient IDs and remove all of those rows across all of my columns within my what was my demo final, which was my 3,641 participants across my 5 variables of interest. I'm going to run that now. Now I have my demo.final1. I've removed 209 observations. Now I'm going to merge it again. So now I'm going to merge MMSE4 total with demo.final1 across all of my patient IDs to get my new merge.df. Now I have 8,138 observations. So it's actually less now than what I could get the maximum number for MMSE4 of 8,227. And that's probably because I have people in my demographic table that do not have MMSE data, and vice versa. And if I don't have a match, then I'm not going to be able to have an observation for that individual or for that data point in my merge.df. So it looks like I only lost maybe a few dozen people here. Thankfully, with a large data set, that doesn't really bother me too much. But nevertheless, that is something that can happen if the IDs do not match exactly or if they're just not present. Okay, now I am going to take my visit code variable within my merge.df, and if I look at my merge.df again, let's just remind ourselves how far we've come. Let's also clear this. Merged.df. So I have patient ID, total, MMSE score, visit code, age, gender, hand, and education. Right, now I'm going to look at now I'm going to reorganize the levels of my visit code so that they're in the chronological order I would expect. Right, they're going to start at screening, then go from 12, 24, 36, and 48 months. If I didn't do this, then it would start at 12, 24, 36, 48, and then screening, and that would be the wrong order. So I have to set the factor now so that the levels match the chronological order I would expect. Doing that, double checking my sanity check yet again. Now it's in the order that I would expect. Now it's time to visualize this. Before, what I had intended to do was to try and visualize this as a scatter plot across all my visit codes with my total MMSE score on the y-axis and then the color of my dots and my regression lines coded as gender, right? So the dots and the regression lines would be one color, and would be one color depending on if it was male or female. And this is a new function that I'm using here that I don't think we've introduced before within our visualization. It's called Geom Smooth. What it's going to do is it's going to fit some kind of regression model depending on what method you use. The default is actually a smooth function, so I'm going to explicitly call the LM function, or the LM method, which stands for just linear model. So I'm just looking at a regression line here. I'm going now to visualize this, and I don't have regression lines. Why don't I have regression lines? It's because I forgot that you can't really plot a regression line with a continuous variable and a factor. I need to have continuous. So although I am happy to see that my data is here, right, it's looking in the way that I expect it to, it's not reflecting exactly what I am hoping to look at. So an alternative could be is that I look at, instead of a scatter plot, as I look at it as box plots across the points, across each visit. And I can't really tell much here. Looks like they pretty much stayed stable across here, but nevertheless, I still want to see my regression line, so I'm going to create a new variable called viscode n. And so this is now where I'm going to convert all of the visits into a numeric variable. First, I'm just going to set it as as NA values across all of them. When I do that, immediately it's going to populate the entire variable with NAs. And now I'm going to use logicals again, where I'm going to say anywhere within viscode that's exactly equal to SC, fill that index with a 0 within my new variable viscode n. So if I run this here and then I plot my new variable again, you can see it's only going to put a 0 wherever there is an SC within my viscode. And then it will do the same thing for 1 for 12 months, 2 for 24 months, 3 for 36 months, and 4 for 48 months. So as I continue to run that here, I can do another quick sanity check. I can see my table for my visit code numeric versus my original visit code. I see that they match up perfectly. So now I'm going to visualize this with regression lines as a scatter plot. And I can see that my regression lines are painfully close to one another, but it's because I have so much variation across all of my visits here. So perhaps to get a better look at if there is any kind of difference here, I'm just going to run another plot without genome point. I'm going to clean it up a little bit by putting more explicit and kind of labels for both my X, Y, and legend axes. And now I can see the overall regression lines that I was intending to look at, where it seems to look at the change or the differential change in MMSE over this 4-year period between females and males. Okay, so that was a lot. Hopefully you take something away from it. I'm hoping that you kind of look at this and you find just one thing that you can be like, man, I've really been struggling to be able to create something or remove something in my data set that would make my life a heck of a lot easier. I just don't know quite how to do it yet, and you can just take that one thing and run with it. I hope that's the case. If not, let me know. I can help you in other ways as well. Otherwise, have a good day. I'll be emailing the code and posting it on Slack to you as well. Again, if you have any questions, I'm here to help. Bye.